All right, the next few days we're going to focus on something called Gauss's law, which is, I think, is misspelled. First thing we'll do is fix the typo. It's A-U-S-S. So Gauss's law, which is a thing that lets us talk about how the field flows through surfaces and is a theoretically very important concept and calculationally also useful in certain cases. Carl Friedrich Gauss is one of those polymaths who pop up from time to time, who leaves his fingerprints all over mathematics and science, actually probably more in math than in science, but contributed this, which is in keeping with some of the other integral results he had from in working on the calculus of integration. So be a little careful, because Gauss's law means different things to different people. To physicists, it means this thing about electric flux we're about to do, but in math, it has other connotations. All right, one of the most important concepts in physics is symmetry, which you've run into. A property is symmetric if it's the same under various geometric transformations, such as translation, rotation, reflection. Actually, in fact, doesn't have to, or other transformations. Doesn't have to be geometric. Fundamentally, symmetry says if you can change something about a problem and the equations don't change, then there's a symmetry that's being respected. We're sort of used to the idea in math class, they'll talk about symmetry like the symmetry of, say, bilateral symmetry, where this half of a person looks the same as this half. Kinda. In biology, it's a little fuzzy. Better probably if we have something like an isosceles triangle, where we can reflect the isosceles triangle down across this red line, and you wouldn't know it if I had drawn a truly isosceles triangle. If you flip it around the perpendicular bisector of the base, you don't know it, which means the symmetry is about ignorance. But it's the thing that lets us use our ignorance to discover other kind of knowledges. Right? One really important takeaway of that, one important use in physics, is that the electric field due to a charge distribution must share any symmetry that that charge distribution has. In other words, if you have a thing where you've got a collection of charges and you can reflect them about a point, and you wouldn't know, then the electric field they produce must also be that you could reflect it around a point and you wouldn't know. And that's just an observational truth. Otherwise, by mentally flipping the points in your head, if that would change the electric field, you could literally detect the change. And a symmetry says there should be no way to detect it. So this will end up being really important for us over the next few bits. As an example, consider an infinite line of charge. The electric field cannot have a component parallel to the x-axis, to the line axis, which I'm doing along the x-axis, I suppose, in this case. All right? Why? Well, it can't be anything like what's going on here, because if there were like this, we could flip the line and you would not know, because the line's infinite, so it's not like one end or the other. You can't tell which side is which. So we flip the line, but in flipping it, we flip the electric field, and that doesn't make any sense, because then we could tell which way this line was oriented, even though the symmetry of it says that we can't. Over here we have on the side the various kind of symmetries that this line has. If it's a cylinder of charge, you can shift it, and if it's infinitely long, you don't know you shifted it, because you're equally far from either end still. You can spin it around its own axis, and you can't tell. You could reflect it about an axis, a plane cutting through it, and you couldn't tell. You could slice it perpendicular to the axis, and you couldn't tell. It also turns out, maybe not surprisingly, that the electric field cannot have a component tangential to the circular cross-section either. It can't point to either side. It also can't point tangential to the cylinder or a circle like it. This is sort of what we're saying, and it can't be like this with this kind of spinning thing, because if we were to reflect the whole world around a line through it like this, we don't know that. The charge hasn't changed any, and yet when we reflect the universe through there, we've changed the orientation of the electric field. So we've detected that reflection, even though we have no way of doing that because the line charge is the same. What we're coming down to here is that we can't perform mental manipulations that produce physical output. Summing this up, and it's an important one, so make sure you understand these arguments, because we'll come back to them quite a bit. The electric field due to any cylindrically symmetric charge has to be radially outward. Right? It must emit outward from the line, directly from the line. And we'll use that quite a bit, and I think it makes sense, but make sure you are okay and on board with that. There are some fundamental symmetries that end up being really useful and occurring at least approximately very often. We can have symmetry in a plane, where everything is confined within an infinite plane and is otherwise uniform about that. And in that case, the field has to be perpendicular to the plane. We have cylindrical symmetry that we just talked about. We have something which is varies only radially, right? Along the line, it doesn't vary. It could vary coming out. And outside, the field has to be radially away from the axis or towards the axis, depending on the charge. And spherical symmetry, which is sort of the granddaddy of all of them and is the easiest to see and happens fairly often. When we have spherical symmetry, then the field can point radially inward or radial outward, but can't have any kind of tangential component. And the idea of spherical symmetry, which you have to keep in mind, is that it doesn't have to be that there's no variation of charge, but the variation of charge can depend only on how far you are from the center of that sphere, and not on your latitude or longitude. And then there'll be some more complex cases that we'll end up using, like a parallel plate capacitor, or coaxial cylinders, or spheres nested within spheres. All right, so let's think through this one. A uniformly charged rod has finite length L. The rod is symmetric on rotations around its axis and reflections in any plane containing the axis, but is not symmetric under translations or reflections in a plane perpendicular to the axis unless that plane bisects the rods. Which shape or shapes match the symmetry of the rod? So let's just take them one by one. Is A possible? Well, if I reflect about this line, the fields look the same. If I spin it, the fields look the same. Right? And if I spin it around that one. And I don't have to shift it, so I'm not too worried about that. And this guy agrees, so this works. How about B? B doesn't work because if I were to flip it, I would end up with field lines that look something like tall, little less, tiny. In other words, I don't get the same field because when I flip it, even though everything looks the same, the field is asymmetric about that pattern. So B is out. C looks very promising because if I flip it, I get the same thing, but I have the problem that when I spin it by some small amount, these will not spin by the appropriate amount, so they're out. In other words, I still need it to be radial. D has both of those things. If I flip it around, spin it around any axis here, spin it around, they come out the same. If I flip it around the axis going through the middle, it comes out the same, and those spin nicely with it, and so therefore D will work. And E is kind of an interesting case. It works for spinning around this axis. It works for reflection around the bisecting plane, but it does not work on this side, but on this side it does not work for rotations, and so therefore this one's also out. All right, imagine we have some opaque box, and we measure the electric field coming out, and it's sketched as shown here. What, if anything, could we say about the charge contained inside that box? Remember that electric field lines start on positive charges, and they end on negative charges. And in our particular case, all of the field lines are coming out of the box, so they must have started inside. So there must be a net positive charge inside. There could be negative charges inside as well, but there must be some leftover positive charges even after we balance off all the negatives that are there. What's the sign of the net charge inside this box? Well, now we have some field lines that are coming out of the box, and we have some field lines that are going in, and in fact as much going in as coming out, which means that on average none of them have been created or destroyed. And so the net charge inside is 0. There's no place, we're not getting any new lines, and we're not losing any lines. We didn't learn very much about the charge in each of those cases, but then again we didn't choose a particularly helpful shape. The rest of this chapter is about picking useful shapes and deriving things about the electric field from them. These shapes that we pick are called Gaussian surfaces, named after the unreasonably prolific and influential mathematical genius Carl Friedrich Gauss. Gaussian surface is a surface, which we mentally conjure, and this is really important. It's a mental surface. It might coincide with a physical surface, but that's not important for Gauss's law. It's just we're in our head sketching out a region in space. Right? It's tough to draw 3D surfaces on a 2D plane, and my art skills are not so great, so we often draw a 2D cross-section and hope that you can sort of project it forward. For instance, we might have a Gaussian sphere. That is a very common one. All right, it's a closed surface around some charge. We usually try and enclose, or at least potentially enclose, charge inside Gauss's surface. We'll see later why that's important. And it's important that a true Gaussian surface is closed, meaning that there's a definite inside and outside, as opposed to, say, a sheet of paper, or a plane, which is open. Right? And it's easier, as they say here, easier to just draw this two-dimensional cross-section, which of course would be a circle. Gaussian surfaces and the Gauss's law are most useful when the electric field has symmetry and your surface matches that symmetry. So here we might have a Gaussian surface that is cylindrical, because all of the electric field is radiating from a line. And so here are our two-dimensional cross sections. Notice we might have to do both. It's not really clear why, to be honest. Oh, from the side. Yeah, from the side, I guess it looks sort of like a square. Right? Cylinders are strange from the side. In a very loose sense, we've seen that electric field flowing out of a closed surface implies a positive charge inside. An electric field flowing into a surface implies a negative charge. But be careful, the field isn't really flowing. Right? Nor do they mark something which is actually flowing. This is a leftover metaphor from the days when people thought that electricity was the flow of charge. The charges were charged fluid going back and forth. In fact, very early on, basically probably until about the early 1900s, people assumed that electricity was some sort of fluid. They also thought heat was a fluid. They thought everything was a fluid. But a lot of the terminology echoes that, even though we now think of it as particles moving that have charge. We'll make this more quantitative by defining something called electric flux, and we summarize it by saying there is outward flux through a closed surface enclosing positive charge, there's inward flux through a closed surface enclosing negative charge, and there's no flux through a closed surface enclosing no net charge. But this is only going to be useful once we define the electric flux, sort of and how to calculate it, which will be the next topic.